I'm really happy to be here. So I will talk today about artificial intelligence and artificial architecture. I will, in fact, ask a few questions. I will not try to bring much answers or, let's say, definitive answers to this question, because in most cases, it's absolutely impossible to do that. So first of all, just like as a precision, I might use the word artificial intelligence in different ways. I don't think it's that important, except for the distinction between symbolic artificial intelligence and connectionist artificial intelligence, as you will see later. But for the rest, what I have in mind when I speak about artificial intelligence today is definitely the most efficient and impressive models, which are, most of you, or probably all of you, know about these models that are generative models, either large language models or other kinds of models. But in any case, this is what I have in mind. Except when I will give more precision. I won't also make any distinction between the kind of work which is produced by artificial intelligence models. It could be videos, still images, sound, text, or whatever. For me, it's not a problem because ultimately, since everything is encoded, it's just a different way to code the information. But fundamentally speaking, there's no difference between coding an image and coding a piece of text or coding some music. It's just about technicalities. Let's call it like that. So one question, the first one, is about the word fitting. We know with these guys that the connectionist models are, by the way, approximators. I mean, when we speak about neural networks that were first invented by this guy in 1943, what we have in mind is nothing else than a model which is trained, obviously, and the training, in fact, consists in adapting the weight of the neural net. And once these weights have been adapted, we can consider that the neural net fits the reality. We call it a reality, but it doesn't matter, by the way, if it's real or not. But let's say the fitting is about fitting something else than itself, obviously. And the whole science of neural network at the very moment is mostly about that. It's about finding the right weights, the right parameters to achieve a much better fitting than what we used to do with classical functions that are not associated with neural nets. As some of you might know, in the past, this guy who invented the perceptron, Frank Rosenblatt, in about 1956, he came up with the perceptron and said that with a neural net, with this kind of architecture, with a weight and a summation function, we can approximate, or let's say we can fit some information. But the problem, the historical problem with the perceptron was that with the perceptron, we could only fit linear phenomenon. We couldn't use the perceptron as a nonlinear approximator. So it was really a mathematical limitation, let's say, a mathematical limit within the perceptron. And this ended up in a way in a very strong critique by Marvin Minsky, who said that because the perceptron cannot approximate any kind of function, it can only approximate linear function, then it's probably not a good model for the future of artificial intelligence. And it explained, by the way, why the connectionist paradigm in artificial intelligence went into a relative, let's say, winter. In fact, the AI winter does not only concern connectionist model, but let's say, in any case, of course, the connectionist model went into some sort of winter because of the critique of Minsky and because many people believe that with a perceptron, with a neural net, we could not approximate any kind of function. So the famous problem was the XOR problem. I won't really go into the detail, but as you can see here with the blue line, if we want to separate the white dots and the black one, as you can see, we cannot use just one linear function. You know, we are forced to make a curve, and this kind of curve cannot be drawn with a classical perceptron with just an input layer and a summation function. And obviously, when we look at what a neural net is doing at the very moment, if I make a very sketchy diagram of what neural networks are doing, they are just separating different kinds of elements. It doesn't matter, as I said, it doesn't really matter what these elements are. But on the most fundamental level, what neural nets are doing is nothing more than that. You have millions and millions of information, and the neural net is making distinction between this information, and the name we give to this distinction ultimately is, like, we call them patterns. I mean, it recognizes some pattern, but basically this word pattern can be a bit misleading because ultimately it's really just about separating different kinds of information. But then with a slightly more advanced model of neural nets, the perceptron with hidden layers, it has been proven that we can go much further and we can approximate nonlinear function. So basically, if I look at another diagram, what is fitting, what is curve fitting or approximation? It's just this kind of stuff. Even if you know nothing about artificial intelligence, and even if you know nothing about neural networks, most of you have already seen these kind of diagrams, you know, because in classical mathematics, the kind of mathematics you learn, we all learn in high school, we are using function to approximate points in space. When we are making use of B-splines, we are also at some point, even if we don't know it, or even if we use Bezier curve or splines for something else. Technically speaking, what these Bezier curves are doing, they are just approximating points in 2D or in 3D space, and then they are B-spline surfaces. So basically, when we do approximation, it's nothing more than that. We have some original piece of information, the dotted line, and we try to find a function which will approximate as well as possible the original data. That's what we are doing when we are basically using neural network. An important piece of mathematical research has been produced in the 80s and early 90s, which is called the universal approximation theorem. It says that with a neural net, we can approximate any kind of mathematical function, which is good because for the people like Minsky in the past, for the people who were strong critics of the connectionist models of the neural net, we finally have a proof about the fact that these connectionist models are mathematically amazingly powerful, because thanks to them, we can approximate any kind of mathematical function. And at some point, it explained quite a lot. I mean, these fundamental results in math explains quite a lot about why the neural net are so amazingly efficient. Because they have the same approximation power as some previous, more classical mathematical tools, mathematical function. But because of the computation of neural net, we can compute with millions or billions or hundreds of billions of parameters, something that would be extremely difficult and that would be extremely heavy and take a lot of time to do with older approximation mathematical models, basically. And here are some other classical approximation models that are used, widely used in 20th century science. Obviously, some of them, like the splines, were mostly developed in the 20th century, but some other, like Weierstrass functions and all of that, came much before the 20th century. When we look at machine learning, these are also approximation methods, by the way, that are not necessarily making use of neural network. So basically, they are more classical model of machine learning. They are not what we call today machine learning when we refer to deep learning, and especially when we refer to deep learning making use of connectionist neural networks. So basically, what's interesting when we look at that, and again, here today, I'm interested in questions. What's interesting, ultimately, is we know that neural nets are approximators. We approximate what happens in the world, basically. It doesn't matter if we want to approximate with a neural net a certain musical melody, or if we want to do weather forecasting, or whatever we want to do. I mean, we want to generate a piece of movie, etc., etc. This doesn't matter. Technically speaking, we can say that what the neural net is doing is some sort of approximation, basically. But the nice thing, and here the conceptual question becomes a bit more interesting, is that when we look at what people say about neural nets, for example, Yann LeCun, there is some debate about what neural networks are really doing, basically. Because we say, oh, they identify patterns. Okay, mathematically speaking, it means nothing. I mean, it's a philosophical statement to say neural nets are identifying patterns, or neural nets are producing, I don't know, like the next, I mean, a nice piece of architecture or a nice piece of design or whatever. I mean, again, mathematically speaking, we need to come up with much more precise answers than just saying it identifies patterns, because this is not a mathematical statement. So mathematically speaking, some people that what deep learning is doing is just glorified pure fitting. And here I will read Yann LeCun. So deep learning is not as impressive as you think, because it's mere interpolation resulting from glorified pure fitting. I won't really go into the technical distinction between approximation, interpolation, etc. I don't think it changed a lot of things here for the argument. But anyway, so some people say deep learning is just glorified pure fitting. And Yann LeCun says, no, in high dimension, there's no such thing as interpolation. In high dimension, everything is extrapolation. Of course, it's some sort of an approximation as well. It's part of the same family, but here there's a distinction between interpolation and extrapolation. Interpolation is that you go through existing points. Extrapolation is that you predict what the next point could be, but the point does not exist, in fact. And so Yann Lequin keeps saying most natural data are strong regularities, which may manifest itself by a nonlinear manifold in the ambient space. But identifying this manifold, so learning a function that can tell you if you are on it or not, is a much harder problem than mere pure fitting. And then some other mathematicians, applied mathematicians or engineers, like Stickley, says, but if, current AI models, if it isn't pure fitting, the curve being a manifold in the high-dimensional space, then what is it doing? And I think that this question, without, as I'm saying here, without even asking almost metaphysical or essentialist question, like what is intelligence? Because it's a much more, let's say, complex question. We might probably not be able to answer this question on a purely technical level. The first question that I want to ask today is based on these comments by Yann Lequin, what a neural net is really doing. And I think if we are interested in more than just producing fancy images, I think it's a very fascinating and very interesting question. What really happens? So this is the first question that I want to open to the discussion, let's say. The second one is about the role of logic in thinking. We know, especially in the Western societies, in the Western tradition, we know that logic has been at the very heart of everything we have done for the last 2000 years at some point. It started with Aristotle, and then obviously it kept running with some very interesting developments, also some winters, very long one, by the way. But logic is at the basis of the Western way of thinking and the Western argumentation. It's obvious when we look at the architectural treatise from the past. It's all about rules. It's all about rules. And by the way, when we write a treatise or when we devise about rules for doing something, what we have in mind, especially at that time, ultimately, is something which is based on the most fundamental laws of logic. And when we look at as you can see, it's also, again, about rules. If we follow some rules, then we shouldn't make any mistake. This is really at the heart of classical logic, of the classical argumentation. We just have to follow the rules, and if we follow the rules, then the result will be fine. There could be no mistake if we follow the rules in the right way, which again is something which is conceptually super interesting. So when we look at the history of architecture, ultimately, we could almost say that it's an history which is derived from let's say, the preeminence or the primacy of logic, which itself comes from Aristotle. Obviously, sometimes things are much more applied. They are more oriented towards pure functionalism. towards industry, whatever. But philosophically speaking, again, what's really at the heart of all of that is a kind of classical way of thinking in a logical way, which is like, we have a set of rules, we follow the rules, and then the result cannot be wrong. This was extremely clear in the Logique de Port-Royal in the 17th century in France, 1662. But obviously, it was also clear in the mind of Georges Boole, who created Boolean algebra, because ultimately what Boole was interested, it was exactly that. It was about extending the logical rules of Aristotle, but we could not make computation with the logical rules of Aristotle. And what Georges Boole was interested was to keep the logical rules of Aristotle, but to allow some sort of calculation based on these rules. And you will see an example of that. So this is a page which is extracted from the famous book by Georges Boole. And as you can see, Georges Boole gives some variable names to these words from the natural language. You know, like X is hard, Y is elastic, and Z is methods, for example. Before Georges Boole, nobody has ever been able to make some computation on logical sentences, you know. So we have to keep, we have to think of how revolutionary this is that. So Boole proposes a sort of algebraization of logics, of language at some point. And he says that the non-elastic methods can be expressed in a mathematical way with this sentence, Z multiplied by 1 minus Y. So, and Y is elastic, it's in form, and Z is method. We could express much more complex sentences, like metallic substances, except those which are neither hard nor elastic. And this is a mathematical writing for this natural language sentence. At some point, probably if we wouldn't have this, we wouldn't even speak of artificial intelligence as we do it today. I mean, but I don't want to go too much into that because afterwards, it's always easy to say, oh, this guy was so revolutionary. Without him, we wouldn't be able to do that, blah, blah, blah. I mean, this can apply to many, many different people and not just Georges Boole, obviously. But what I'm interested in here is, again, the role of logics. And logics, as David Hilbert said, is a hygiene of mathematics. But more importantly for us, what's interesting is that logic, or at least classical logic, is a way to acquire certainty. Because that's probably the way we are wired. You know, that's probably the way our brain has been built. I mean, it's very difficult to know something for sure without making use of the rules of logical inferences. I mean, some people say this is a fake, you know, and it's a fake image, by the way. But who knows? Maybe it's not, maybe it's true. I mean, maybe it's a real image, you know, we don't know that. So basically, conceptually speaking and epistemologically speaking, what's really interesting in the shift from good old-fashioned AI, which is symbolic AI, which is based on the use of logical rules, and the current deep learning models of artificial intelligence, is that the first one are making use of logical rules, and the second one are making use of just probabilistic mathematical information. And because there's no logical rules in the second one, ultimately, we cannot really decide for sure about the nature of this image. Again, it's definitely fake, but we don't have logical arguments to say that it's fake. Okay. So the certainty is missing. The certainty is missing. So obviously for architecture, for the discipline of architecture, it's probably not really a big deal, But intellectually speaking, conceptually speaking, if we try to address the issue of artificial intelligence beyond architecture, then it's a very it's a very problematic question. The fact that the rules of logic are missing in the latest artificial intelligence model. Just as a side note, we have to keep in mind that the use of classical logical rules was not going completely smoothly, let's say. For example, in mathematics, the intuitionists, they were highly critical about the use of classical logic. At some point, we could say, I wouldn't say that the foresaw what's happening today, but the fact that they did not accept some of the classical axioms of logics is a very interesting thing. So I just engage you in looking at that problem. I cannot speak about this. It would be much too long. But anyway, at the beginning of the 20th century, as you can see, for example, in the famous work by Carnap from the Vienna Circle, Carnap was one of the most extreme proponents of logical positivism or logical empiricism. It depends. The Vienna Circle was sometimes associated with logical positivism and sometimes with logical empiricism. But when we look at Carnap, we see that for Carnap, the right way to know about the world, the right way to build a new world, a world which would be based on some truly interesting facts, actually, is by making use of logical rules. So Carnap wanted to reduce the world to a set of logical rules and to some logical structure. And it's not just the world that was supposed to be reduced to logical structure, it's also the language, as you can see here on the right. In architecture, more or less at the same time, in the Netherlands with the elementarism, with Rietveld and Van Desburg and a couple of other radical artists, including Mondrian, but Mondrian took some distance with that. At some point, he chose his own path. But when we look at what happens in architecture in the year 1920s, it's very much, it's super close to what happens in logical positivism. It's really about making use of minimal set of logical rules. You will say, oh, it's not logical. It's not logic here. It's just geometry. Okay, right. But conceptually speaking, they were not interested in geometry. And by the way, the very fact that they are not making use of traditional perspective and all of that is a proof that they were not interested in classical geometry. They were interested in some sort of more abstract form of geometry, and this geometry could be reduced to logics. So then this logical approach, it kept being used in the discipline of architecture. And by the way, the more it evolved through the 20th century, the more academic and boring and conservative it became. Until this book by Christian Norbert Schulz, which at some point is making some hypotheses about the fact that, again, if you use the right set of logical rules, then you will end up with good architecture, which is wrong, obviously. The same happened with Christopher Alexander. Christopher Alexander believed that the world of architecture could be reduced to patterns. So we could say, okay, patterns are not exactly like logic, which is true, but ultimately, conceptually, the path that was followed by Christopher Alexander was definitely the path of the kind of logical thinking that was developed at the beginning of the 20th century. Peter Eisenman also, with the formal basis of modern architecture, tried to address the different problems in architecture in more or less the same way, but the difference between Eisenman and Christopher Alexander is that Eisenman was using logics and formalism as a method. He never let's say, made the kind of inference saying that if you follow the rules, you can end up with good architecture. You know, what he said, in a way, was we should follow the rules because these are the rules of the Occidental thinking. Does it make good architecture? No. But still, let's do it at some point. So, I mean, I make it very simple here. Obviously, you have to read Peter Eisenman, but it's clear that Peter Eisenman never believed in such a simplistic vision of architecture for which, if we just follow the rule, we will end up with masterpieces in architecture. This is absolutely wrong, and Peter Eisenman knew that, obviously. I tried to address this problem, by the way, in the exhibition that was mentioned by Maya in 2007 in Marseille, in the south of France, by showing the relationship that could exist between some work by Eisenman and some other work by more recent architects. It was the first time that the brick wall by Fabio Carmadio and Matthias Köhler was ever exhibited. Yeah, but okay, just a side note. Speaking about logic, the logical paradigm in architecture, which correspond to the symbolic paradigm in artificial intelligence, was still in use, or not just in use, but it was really under strong development in the 70s, at the end of the 70s, with this book, which was published in 1978, and also with the invention of the shape grammars by George Steiny. The approach of Cédric Price, the approach of Nicolas Negroponte as well, at some point were also so not radically logical, were also following the path of a logical thinking in the 20th century architecture and let's say philosophy of mathematics and philosophy of science. And again, I mentioned that because at the very moment, because of the probabilistic paradigm, what we are doing at the moment when we make use of artificial intelligence is so amazingly different from all of that. So things based on the on logics, things based on language, and things based on the logical rules of language, which is a kind of synthesis between mathematical problem and language-based problems, are now disappearing. And this is why I proposed quite a long time ago this classification, let's say this for computationalism, which is not just expressing the fact that we use a computer. It's just expressing the fact it expresses something more global. The fact that the way we think as humans, the way we developed rationality and rationalism in the history of Western thinking is now, let's say, fragile, or it disappears in favor of some approach which are all based on the use of computation. So it's computationalism. And the fact is that because of that, what happens is that if we change the model of computation, then we might change the whole signification, for example, of what computational neuroscience is. But just not computational neuroscience, but all of that, you know. I mean, all of the disciplines today are becoming so dependent on computation that what matters is the model of computation we are using. Because if we change the model of computation, then we change the whole definition of such or such a discipline. So the use of language and the use of logics, as I said before, it goes back to Aristotle. Aristotle, who said in the prior analytics, a discourse in which certain things having been supposed, something different from the things supposed result of necessity, because these things are so. So the important word is, obviously, it's result of necessity. As I say, I mean, something is a necessary consequence of something else. Very classical examples of that are the syllogisms established by Aristotle. For example, this one, you know, with the existential universal quantifier and existential quantifier. So universal quantifiers are all. This is the universal quantifier, and this is an existential quantifier, so universal for all x. Existential, there is one x, at least. It could be more than that, with such or such. So classical examples of the use of logical rules was about analyzing sentences. You know, you take the original sentences and then you ask logical questions. As you can see, does the lawn need mowing? Okay. Do you have a mower, gas, electric, push, etc., etc.? This ultimately is a logical diagram. You know, you ask logical questions that you can answer with yes and no, and then based on that you analyze the sentence and you can infer some result. The whole analysis, the whole work of Noam Chomsky is based on that. You know, it's the syntactic structure of Chomsky intellectually is based on a logical understanding of what language is about. And as we will see, this is not what's happening today in artificial intelligence. Chomsky, by the way, the classification of Chomsky allowed also to be much more precise when we had to speak about programming languages. So this idea of logics, it's also at the heart of the computer, thanks to the logic gates with a minimal set with NAND and NOR. It's a logical functions which I mean, either NAND or NOR are logical functions that are, let's say, enough to build a universal computer, but we can also use AND and NOT or NOT, etc. And when we look at some old-fashioned model like ELIZA, one of the early and super famous models of artificial intelligence, the symbolic artificial intelligence, it was a conversational chatbot. What we see is, again, that all of that is based on a logical understanding of language. We can see this as well here with this kind of relational diagrams, and here as well. So what's interesting is that when we put this to the limit, for example, here, we have this kind of SAT formula. So we can reduce, for example, an extremely complex sentence or a piece of text. We can reduce the piece of text to an amazingly long and complex SAT formula, which is a logical, it's a piece of pure logic, by the way. This means or, this means and this means not. So this is the classical way language was analyzed before the advent of large language models. But with large language models, this is an example of it here, of ChatGPT, ChatGPT 3. We are not making use of logics. We are making use of a concept, which is called the tokenization. Okay, the tokenization. And what we are looking at are tokens. A token can be more or less anything at some point. The model, the artificial intelligence model, the neural net, is learning what is the best representation of the tokens, producing the most interesting and accurate result. But ultimately, we make use of this concept of tokenization, but I will get back to it a bit later. So what happens is that in the 70s, with postmodernism, people started to understand that we were a bit trapped in what they called, for example, Frederick Jameson here, the prison house of language. Some people, like Charles Jenks, also started to understand that the language of modern architecture, for example, as it was established by Bruno Zevi, was probably not the right way to deal with the complexity of architecture. But the problem is that, as you can see here, Charles Jenks replaced the modern language of architecture by the postmodern language of architecture, or let's say the language of postmodern architecture, which is not that different. Some other architects like Rudolfsky started to understand that ultimately there could be something in architecture that could be not just depending on linguistic problems. So Rudolfsky was also interested in some sort of emergent architecture, very much like what we have here, but also very much like what would happen in the early 90s with Stan Allen and with some other architectural theoreticians like it. So in the postmodern, in the postmodern thinking, we started to see, let's say, a kind of distanciation from the classical understanding of architecture as a linguistic problem, either a modern problem or modern language, or postmodern problem and postmodern language. So some other discipline started to enter, like ecology, ecology of mind, and not just classical ecology, like the evolution. I mean, chaos theory, evolution theory, etc., etc., and obviously some algorithmic approach that were um, that enter also the discipline of action. So what we have here is a small synthesis of the kind of thinking we can have when we address architecture, but not just architecture. It goes obviously beyond that. But with the computer, with artificial intelligence as we know it today, what we see is that we have some amazing performance coming from new kinds of models. We don't know everything about these models, but what's interesting, as Richard Hamming said in 1980, is that this model, it seems to us that they are developing their own kind of intelligence, but obviously we don't really understand exactly what happens with this. But we need, maybe for the first time in the history of humankind as we know, as we used to know it at some point, maybe we need to address the possibility of some higher form of intelligence and the possibility of unthinkable thought. By unthinkable thought, what Hamming says here is that unthinkable according to the classical paradigm of thinking, the one of rationalism, the one which is based on the use of logics as we know it in the last 2000 years. So I will end up with this. So I spoke about Chomsky. I spoke about Chomsky, and I spoke about the fact that for Chomsky, we need to run a logical analysis of language. We need to understand the language as a piece of structure, as something which is extremely rigorously structured. And for Chomsky, if we don't understand the structure of language, if we don't understand, for example, the kind of trees that we can build when we build a sentence, there's no way we can come up with something which is interesting. So let's look in this recent article by Chomsky, The False Promise of ChatGPT. Let's look at the argument of Chomsky. Chomsky says that we should at some point be optimistic because intelligence is a means, so easier here, by which we solve problems. We should have concern because we fear that the most popular and fashionable strain of AI, which is machine learning, will degrade our science and debase our ethics by incorporating into our technology a fundamentally flawed conception of language and knowledge. Okay, the fundamentally flawed conception of language and knowledge, what does it mean for Chomsky? It means something which is not based on logics. It means something that cannot bring certainty. Something for which we can invent meaning, but we can never really be sure about what the meaning is about, but also if, for example, for such or such a fact, if it did exist or if it doesn't exist. So for Chomsky, it's absolutely fundamental to understand that language, knowledge, and truth goes together. And the way we put all these things together is by making use of logical rules. And Chomsky keeps explaining his way of looking at artificial intelligence. So he says that the Borgesian revelation of understanding has not and will not, and we submit, cannot occur if machine learning programs like ChatGPT continue to dominate the field of artificial intelligence. However useful these programs may be in some narrow domains, okay, we know from the science of linguistics and the philosophy of knowledge that they differ profoundly from how humans reason and use language. So how human reasons and use language is, again, by making use of inference rules that are the classical logical rules of inference. These differences place significant limitation on what this program can do and coding them with ineradicable defect. And then he says it's at once comic and tragic, as Borges might have noted, that so much money and attention could be concentrated on so little a thing, something so trivial when contrasted with the human mind, which by dint of language is a word of von Humboldt can make infinite use of finite means, creating ideas and theories with universal reach, etc., etc. So basically, for Chomsky, the human mind is not, like ChatGPT, a lumbering statistical engine for pattern matching. So when we follow the argument of Chomsky at some point, what's interesting is that Chomsky says that despite the fact that these models like ChatGPT are amazingly efficient, that they provide amazing results, we cannot consider this in any way as an expression of intelligence, and not even an expression of anything. I mean, for Chomsky, it's just statistical gibberish at some point. So he says that such programs are stuck in a pre-human or non-human phase of cognitive evolution. The deepest flaw is the absence of the most critical capacity of any intelligence to say not only what is the case, what was the case, and what will be the case. That's description and prediction. Those are the ingredients of explanation, the mark of true intelligence. So basically, for Chomsky, the fact that these models are not making use of the classical rules of language and the way we understand language in a logical way makes this model absolutely useless. And it takes as an example the fact that if you ask some specific question to ChatGPT, like John is too stubborn to talk to, ChatGPT does not understand the subtlety of this kind of sentence. So I just asked this sentence to ChatGPT, and in fact, ChatGPT understands absolutely perfectly what it means. So he says that John is too stubborn to talk means that John is so stubborn or uncooperative that it is difficult to have difficult or frustrating to have a conversation with him. And this is the answer that Chomsky had in mind, but he believed that ChatGPT could not give a satisfying answer to this kind of highly ambiguous sentence. So either we do it in ChatGPT 3.5 or ChatGPT 4. Actually, the answer is extremely satisfying. So ultimately, what we see here with this example and with so I will let you read in depth the original article by Chomsky, and you will probably find your own argument as well. But what's really interesting is that the efficiency of ChatGPT, in fact, comes from the complete lack of understanding of what language is about. So because there's no linguistic concept in ChatGPT. There's only probabilistic figures, actually, but there's absolutely no linguistic concept in ChatGPT. So for Chomsky, true intelligence is demonstrated in the ability to think and express improbable but insightful thing. This idea of making use of things that are not based on linguistic is also at the heart of the latest work by Mario Carpo. I will let you look at the work by Mario Carpo. But ultimately here, what I'm really interested in is the fact that the very high quality result of models like large language models and any kind of generative model comes precisely from the fact that they are not making use of the classical rules of logics and neither of the classical understanding of what linguistic is about. So for us, it's a bit, let's say, puzzling, because everything we believed that was, let's say, obvious in the past, the fact that for 2000 years, if we want to understand what intelligence is about, if we want to understand what truth is about, and if we want to understand what language is about, we had to make use of logical rules. And ultimately, by choosing a complete opposite approach, by not making use of these rules, we end up with extraordinary, interesting and efficient result. So this question here is really about what is the role of language in architecture, because as you saw, until the very end of postmodernity, architecture was devised in terms of language. I mean, for Charles Jencks, it was a matter of language, and even for deconstructivist architecture, it was also a matter of language. We are now entering a phase in the history of architecture where we don't speak about language anymore because it's not an important question, and because, as we saw with large language model, forgetting about language is the approach which is precisely giving the most interesting and the smartest result. I want to end up with this question very quickly about creativity. And I just wanted to say, so all of these examples are created by different architects making use of Midjourney or some other models. Again, it doesn't really matter the exact type of generative models which are used here. I want to end up with the problem of creativity, which is classically defined as something that we don't expect at some point. So creativity is in most cases defined as the capacity to produce something that was not expected, something surprising. It's a very classical way of defining creativity, but it's also a very classical way of defining information. If you know a bit about the theory of information by Shannon, you would see that the quantification of information is based on the uncertainty and the surprise, the quantity of surprise which is attached to a piece of information. So it's as I said, it's a quantification of surprise at some point. So when I look at all of that, I mean, all of this is produced by AI, by the way, including this what I call the super baroque examples like this. When we look at that, I mean, we might have a tendency to ask the question about creativity. I would say, for me, it's not the most puzzling or the most interesting question, conceptually speaking, for different reasons. Is that first, as Hinton said, deep learning is going to be able to do everything. So if it can do everything, it can produce any kind of unexpected result. So the question of creativity at some point, I mean, we won't really be able to answer this question because we will endlessly have unexpected result. And just to say that creativity is about producing unexpected stuff won't be enough. You know, I mean, it definitely won't be a satisfying answer. So I would say that the question of creativity is a wrong question. It ultimately refers to knowledge and intelligence. Since the only thing that computers know are information of computation, we should ask the question of creativity not in terms of unexpected information, but we should mostly ask what's really happening in the computer. So we should move from the question of creativity to the question of knowledge and information. From it's definitely more important. So I won't go too much into that. We should ask ourselves, how much information do we need to be able to identify something? Obviously, we cannot identify Barack Obama here if we didn't know Barack Obama before, which means that at some point, to address the quality of something, including something that might be creative, you need some pre-existing information beforehand. And then the definition, or let's say what this pre-existing information is about, is something which becomes extremely important. We should ask about it. And finally, which is maybe the most destabilizing question for me, is a question which is absolutely probabilistic. I'm sure you have seen these images everywhere. You know, I mean, this portrait, these people are part of the series. These people do not exist. You know, this person does not exist. So you have thousands or already hundreds of thousands of examples of faces online, which are purely artificial faces. So obviously this person do not exist, you know. But if you really look at this in a purely probabilistic way, and this I think it is extremely destabilizing, it might be the case that the probability for this person to exist somewhere in the world is incredibly high. So we produce images of people who are not supposed to exist, but because of the pure math associated with the neural network, and I mean, it's just raw, basic probabilistic theory of probability. It might be the case that there is more chance for this person or this person to exist in the world that, let's say, for the weather to be sunny or rainy tomorrow. So I think, you know, so then the question of creativity, the classical way to ask about creativity would be, oh, the artificial intelligence model is so creative. It can create faces of people who do not exist, and look how amazing it is as they really resemble like real people, etc., etc. And if you look at Margaret Button, for example, this is a kind of analysis of creativity she's running. She's looking at combinatorial creativity, exploratory creativity, transformational creativity, etc., etc. But there's a question she never asked, you know. And by the way, it doesn't really matter which model of creativity we are speaking about. The other question she does not really ask is, what happens is the probability, if the probability for the real existence of the output For example, again, the probability of the existence of this guy in the world becomes extremely high because machine learning models are probabilistic at the moment, like ChatGPT. I mean, you might ask something to ChatGPT and it can end up with a piece of discourse. And just again, with pure math, you can check that maybe this discourse already exists somewhere in a book in the world, you know, in a certain piece of book, in a certain library, etc., etc. And this applies to this kind of production as well. So here, for me, there's a deeper question which is associated with creativity. It's a question of existence. What happens if what we used to analyze in terms of creativity, we now have to analyze those things in terms of the possibility of the real existence? And it seems to me that it's a very it's a very weird question when you think of it. Again, it's a very weird question because then, rather than creating images, we could say that artificial intelligence models will create a completely new form of reality, and not just a kind of simulated reality. I mean, something real, you know. At some point, again, it can create an individual. It can create the image of an individual which exists somewhere. And I wouldn't be surprised in a few years to see some guy coming and say, oh, I've seen my image online, you know, but this image has been produced by an artificial intelligence. Yeah. So, yeah, I just want to end up with this, with this really weird question of what are we doing when the models of today are so good that they can predict the existence of something with a probability which is almost 100%. What happens? And ethically speaking, and again intellectually speaking, I think it's a very weird question we are not ready at all to address. So yeah, I want to stop here.